that whatever, after substituting this psi in this equation, the final result will not depend on the parameters of the motion. In fact, as I mentioned in the previous slide, you can see that earlier the wave equation governing the electromagnetic plane waves, when used for solving the Schrodinger wave equation, then the parameters will depend on the system, it will depend on the state of system can be get rid of if we use the above mentioned equation. Nebula square psi is equal to 1 by v square del psi by del t. But then another problem has entered into the problem, that this solution, this velocity and the state function psi, that will be now complex quantity. So, being a complex, now we have to be a little worried about it, because we know that everything which is happening around us, even at a microscopic level, it should be a real thing, and therefore one has to extract some real information from this mathematically originated complex quantity. So, at this juncture, I will say that the complex nature of the wave function psi is by virtue of mathematical treatment, which is required in order to get rid of the parameters of the equation independent of the state. So, our next task is obviously to understand that if psi is a complex function, then what should be its interpretation, and how is it able to solve the physical problem, and how is it able to give some physical concepts of the systems. So, we go further with the two experiments. One we can say which is a very well known experiment even at the school level, and that problem experiment is the double slit experiment. Particularly the double slit experiment performed with the light, or you can say the radiation. As shown in the figure, let us say that some plane waves are incident on the two narrow slits which are kept very close by, and let us also assume that this incident light waves are in fact the you can say the coherent. So, their coherence nature will allow us to see the permanent or the stationary pattern on the screen, and as it is shown in the slide, you can see on the screen that dark colored and little bright red fringes are observed. So, what we conclude from this double slit experiment of the light, that on the screen we have intensity distributions. There will be a dark fringes where the intensity is a minimum, very small, or 0 for practical purposes. There will be a region where the bright fringes are shown. So, we say that while performing double slit experiments, light or the wave, then on the screen we have a intensity distribution as mentioned here, that intensity I at a position r at a time t, which will be governed by the absolute square of the electric field. For the just sake of completeness, I show the few back slide. You can see on the slide that I have mentioned what is electric field E. So, when I find the modulus of E as shown in the figure, as shown in the equation, then this exponential term having the complex factor I will get rid of, and eventually this mod E square, which represents the intensity, is the real quantity. So, even if this definitely tells us that even if your function E is complex in its own, but the intensity distribution, which is the real physical quantity which we are observing on the experiment, being observable, it is a real quantity. So, that gives us a confidence that no problem, even if your function psi is a complex quantity, but if we find the way out like this, that if we find the modulus of psi, then that quantity, modulus means you know that it is its multiplication of psi with its complex conjugate, then that will be the real quantity. So, if we go in a analogous to this, in a similar way to this double slit experiment for the light, which tells us that as light is distributed, its intensity is distributed on a screen, and it can be calculated by the modulus of the electric field, the function E. Similar to this, if we perform a hypothetical double slit experiment for the photon, though I have used the phrase hypothetical, but practically also such experiments can be performed. For example, if we reduce the intensity very to a very small amount, so that as if at a time now only one photon, one bundle of energy is coming out of the slits, then it can be visualized as the separate or discrete energy quantum, and that quantum, as you know, is known as the photon. So practically also within certain limit of error, we are also in a position to perform such experiments in which, rather than having a large intensity, the complete beam of light, we can illuminate two slits by the very weak, or you can say the very less light, so that it will behave like a separate photon. And such photons, when are been received on the screen, then what it gives is been picturized. In fact, this is the picture of the hypothetical or the mental double slit experiments, in which the white spots on this screen are basically showing that this were the photons who on the diffraction comes and strikes the screen. Whereas we can see now we cannot talk about the intensity, we should talk about the positions. Our more fundamental question to this experiment should be where the photons will strike. What will be the position of the photons on the screen after diffraction? So obviously in such experiments we are in fact interested to the positions of the photons rather than talking about the intensity distributions. So that gives us you can say the intuition, that gives us the inner feeling that whenever you talk about the particles or the photons, then for that during the diffraction experiment we will be able to calculate the position rather than finding the intensity distribution pertaining to the wave nature. So with to analogous to the previous slide, where when we have shown that how light is diffracted, then intensity distribution is obtained on the screen, we now can talk about the probability distribution of the position of the photons. As you can see from the pictorial representation, that the spots, white spots, are basically showing the positions at which the photons on diffractions are received on the screen. So obviously this is the first, you can say that the experimental evidence, hypothetical though, can suggest that we may talk about the position probability rather than the intensity distributions for such a particle diffraction or the photon diffractions. But we know also from the previous experiments by Planck's while studying the black body radiation or the photoelectric effects and other experiments performed by the other group of scientists, they have shown that for such a microscopic particles, the position and momenta together cannot be in general precisely measured. Similarly, we cannot measure the energy and time very precisely. There is always associated some uncertainty in it, and we know that this is the very well known fact proposed by Heisenberg, that it is the uncertainty principle who prevents the exact and very precise simultaneous measurements of the position and the momentum. Similarly, we may not get the very precise measurement at a time of energy and time. So we can say that this uncertainty principle allows us to talk about the probability distribution. The word itself is very illustrative, that we are not sure about the exact position of the photon. Where on a diffraction photon will strike the screen is not a correct question in quantum mechanics. We should ask rather more accurately, correctly, that what will be the probability that the photon will strike to the screen, with what possibility, what are the likelihood of the photons to be received on the screen. So this intuition, this hypothetical nature, hypothetical experiment suggests that the wave function should also be interpreted in a statistical way, in a probabilistic way. With the previous experiment, now we can say that the function psi is in fact is the measure of probability. It talks about the probability of the position of the particle which is received on a diffraction on the screen. So psi, it's a first interpretation I am just proposing, that psi is the measure of the probability. But we also know that probability cannot be negative, it cannot be even complex. Probability is always real and it should be greater than 0. If we are dead sure about the position of particle, the probability will be the 1. If we are dead sure about not having a particle in a given space, then we say that the probability of finding particle is 0 or null, or otherwise the probability ranges from 0 to 1. So we have a physical constraint that the probability cannot be negative, it cannot be complex. Then problem is that we say that psi is the measure of probability, and we have already noticed that psi mathematically is complex in nature. Then how this complex nature of a psi gives us the probability? The way out of this difficulty is that psi may not be the real quantity, but its absolute square, its conjugate multiplied by its own, will give the real quantity. And therefore now we assume that the probability p at a function r, at a position r, at a function t, can be used to define the position probability density. So let us say psi, which is of course the measure of probability, but the actual value of the probability can be calculated by its absolute square. So we have now defined with this mental experiment that the function psi multiplied by its complex conjugate, that is psi star psi, is in fact giving the position probability of finding a particle at a space r and at a time t. After you can say this statistical notion, statistical idea to how to describe the function psi in a probabilistic way. Now we go back to the Schrodinger equation. Just have a look at that equation. This Schrodinger equation, when is solved, then it also demands, see, this is the Schrodinger equation, just for the reminder, that when this equation is solved, then it also demands certain mathematical as well as some physical constraints, physical conditions. What are those conditions through which we can again get more insight to the wave function and we will be able to understand the function psi in detail? Looking to that equation, definitely we say that the Schrodinger equation is a first order differential equation. Then as a curious person, we may ask that why it is a first order equation, why not second order or the higher order differential equation is used? It is mathematical in nature. In fact, whenever we have a first order differential equation, then while solving this first order differential equation, it is always possible and it gives a mathematical ease also to solve first order equation by employing the initial conditions. What will be the wave function psi at initial time t equals to 0? So if we know about the wave function at a t equals to 0 time at a position r, mathematically, if we know what is the wave function psi r of 0, then we'll be able to solve the Schrodinger equation even at a later time. So being a first order differential equation, the time evolution of the wave function can also be calculated. So this is the advantage, a mathematical advantage, or you can say that mathematical requirement, that we keep the wave function to the first order, so that the solving of first order linear equation gives us the idea about the later time also. Second property, mathematical property, which we seek in a Schrodinger equation, that it should be linear. Linear word in mathematics, that linearity means will be able to make a linear combination of such a wave function. Let us say that our some system is been described by many wave functions, psi 1, psi 2, psi 3, psi 4. If they are all the solution of the Schrodinger equation, then this linearity suggests that even their linear combination is also the solution. That means if we have some constant C1 multiplied by psi 1 plus C2 multiplied by psi 2 plus C3 multiplied by psi 3, like this, then this linear combination will also be the solution of the Schrodinger equation. So this linearity suggests or demands that the wave function, if it is linear, then their linear combination will also be the solution of Schrodinger equation. And this is needed, particularly the physical requirement justification to this linearity comes from the superposition principle. We know from the elementary discussion that the particle nature of the radiation or the matter wave in fact is not described by the single wave. Rather than we describe those particles using the wave packet, or you can say that it is the packet of waves, the bundle of waves. And whenever there are more waves superimposed at the one point to describe the some microscopic system, then what it leads to the superposition of waves, or you can also say the interference, because now waves will impose at a point at a time, then they will create the interference effect or the superposition effect. So where we come across that many wave functions, many waves are being used to describe the wave packet, and therefore we mathematically as well as physically requires that the more than one waves are used to describe such situations. So obviously physically also we are in a requirement that there should be more than one waves and their linear combination